Welcome back to part 2 of Module 10, Lesson 2, where we're continuing our study in relative frequency of simple events. This time we're going to be taking a look at this bar graph we have here, and the graph shows the results of an experiment in which a spinner with 3 equal-sized sections was spun a number of times. Find the relative frequency of spinning a green or blue in this experiment and express your ratio as a fraction is what they're looking for. Now if we zoomed in here, we can see some pretty good details on this. We can see that the red won 14 times, the green won 24 times, and the blue, it ended up winning 22 times. Now if you think about it, those were equal size, so it should have been even all the way across, but just because it should have been doesn't mean it's going to be. Life isn't fair, even if you're living a spinner's life. Probability does not always, experimental probability and the other probability, which names escapes me right now, do not always match out. So first we're going to study the graph to determine the frequency of the outcome of each, and we just talked about that, and we can see here that, let it load up. We can see that there is 14 green. We said that there was going to be 24 red, so I'm sorry, 14 red, 24 green, and 22 blue. And from there, we can take and check that. That part checks. Next, it has a relative frequency of the number of green and the number of blue to the total number of spins. Well, there is 24 green. There's 22 blue that you can see down here, and there was 60 spins total when you added them all together. So you take from there 24 plus 22, that's going to give you 46 over 60, and 46 over 60 of course ends up simplifying to be 23 over 30. So let's put that in as our fraction, 23 over 30, where I divided the two numbers by 2, hit accept and check. And the answer checks. So the relative frequency of spinning a green or blue is 23 out of 50 or 30. It's easy, that easy. Now it's going to be your turn to do extra example number 3, where you have a graph that shows the results of an experiment with a spinner with 4 equal sizes that were spun. Find the relative frequency of spinning a number greater than 2 for this experiment. Express the ratio as a decimal. Go ahead and pause the video and do that. First off, we need to figure out which ones meet the requirement. And the ones that meet the requirement, that is going to be 3 and 4, because 3 and 4 are going to be the numbers greater than 2. If you look closely at the graph, the 3 ended up occurring 22 times, and the 4 ended up occurring 20 times. Now I'm going to set up my formula, which I have said just to do number of favorable outcomes over total outcomes. The number of favorable outcomes is going to be 22 plus 20, and the number of total outcomes, well, let's go ahead and add them up down here. I have a 26 for 1, a 32, plus the 22 and the 20 right there. When we add those up, on top we're going to get 44, and on the bottom the total number of outcomes we had, well, 22 plus 26 plus 32, that's going to be 58, and then there we have 60, 70, 80, and then after 80 we're going to have 90, 100. So there was 100 spins made total. That we could simplify, but we don't really need to because the question wants it as a decimal. And 44 over 100 you could read as 0 and 44 hundredths. And at that point, you're done. Jump back over to our textbook, type in our answer, 0.44, check our answer, and I must have had some bad math. Let me check it. I did have a little bad math here. That happens sometimes when I'm running my mouth. This number right here, that should have been a 42 over 100, which means my answer should have been 0 and 42 hundredths. Sometimes I talk more than I think. You have that problem? Suppose 100 randomly selected people are asked their blood type. The results are shown. To find the relative frequency ratio for each blood type, you're going to find the ratio of the frequency, which is going to be the number of people for each blood type, to the total number surveyed, 100. So blood type A was 40 to 100, AB was 5 to 100, B was 10 to 100, and O was 45 to 0. You can show the relative frequency of the data in a frequency table. So here we have a definition that says this is a kind of table that lists both the frequency and the relative frequency of the data. Right here we have the frequency, but we don't have the relative frequency yet. So we need to create that in order to do it. So with the blood type of A, it was 40 out of 100, which they put as a fraction, 40 out of 100, also known as 4%. And then the B was 10 out of 100, which they listed 10 out of 100 here. 10 hundredths is also going to be 0.1 or 1/10. 5 hundredths, that's going to be 0.05. And then 45 hundredths, I'm honestly shocked that O's that high. That's going to be 0.45. Check your answer. That should all be easy math, things you're very familiar with doing from when you were little kids. You can also graph the frequency values of a table on a relative frequency graph, and this is a kind of bar graph that shows the relative frequency of the data. So now we've got our decimal values here, and they went ahead and made the tenths into hundredths, so everything's kind of the same. And they said graph the relative frequency for each blood value, a blood type, by shading the sectors of the bar using a scale of 0 to 0.5 for the relative frequency values, because the greatest value is 0.45, which is going to be less than 0.5. What they're saying there is they stopped at this number 0.5 because right here, that's going to be their biggest number. So type A was 0.4. So we got our color selected, and we're going to have to shade all of these bars from 0.4 down. Type B was 0.1, which means that bar graph is going to look like that. Type C, no, excuse me, type AB, there's no C. Type AB is going to be 0.05, which is right there. And that's a category I'm in. Didn't know it was that rare. And then type O, they said is 0.45, so we're going to run this one almost all the way up to the top, and it's going to go right there. Check your answer. That's what your bar graph is going to look like. I don't think there's any new, great, amazing revelations that came out of that lesson, or that part of the lesson. Now let's take a look at experimental probability. A relative frequency of an event can be useful to predict the chance an event occurs in the future. The chance the future event will occur is based on the experiment's result, and that's called your experimental probability. Another vocab word. Lots of vocab words in this lesson. It has the same ratio as the relative frequency. So your experimental frequency is going to be the same as your relative frequency according to this. Looking at it in words, the experimental probability is the ratio of the number of favorable outcomes to the total number of outcomes. And then as a ratio, you can see number of favorable outcomes divided by the total number of outcomes. That's going to give you the probability of the event. The P event means probability of the event occurring. Suppose Amelia is presented with two unmarked boxes of the same size. Amelia opens the first box, in which there is a present. She opens the second box, and there is no present. So sad. The relative frequency of selecting a box with a present inside is 1 out of 2, also known as 0.5 or 5/10, also known as 50%. The table compares and contrasts the relative frequency and the experimental probability here. So the ratio of the number of favorable outcomes to the number of total outcomes, that was the 1/2 we came up with right here. And then the differences here, so that's the similarities between the relative frequency and the experimental outcome. And the differences between them is that describing the relative frequency describes an event that has already occurred. Meanwhile, the experimental frequency, that is an unknown thing. We're thinking that's what's going to happen in the future. We can't prove it, but based off of the past events, we're going to have the same thing happen in the future. The relative frequency is occurred. It's a known value. Experimental frequency, we're hoping it's going to happen that way again, but it's not a guaranteed thing. So example number 4 says to refer to the relative frequency bar graph. What is the experimental probability that a person chosen at random from a group is going to have type A or type B blood types? Well, that's going to be the same as the relative frequency of them having them both type A and type B. Find the relative frequency of A or B, and the relative frequency of type A or type B is the sum of the relative frequencies of each of them. So you can see A was 0.45 and B was 0.1. So move through the steps here. We're going to take and add them up. The 0.45 plus the 0.1. I'm going to check that. Okay, 0.40 plus 0.1. Good. And those, of course, add up to be 0.5 or 0.50. Good. And now we can say that because of that, the experimental probability has the same ratio as the relative frequency. So the experimental probability that a randomly chosen donor is going to be of type A or type B is going to be 50%. See how easy that is? Now it's going to be your turn. Pause your video and work on extra example 4 on your own. A random selection of students in 3 different classrooms was asked a question: what is your favorite season? The results are shown in the graph. What is the experimental probability that a person chosen at random will select spring or summer? So we're going to take and get our screenshot of our problem here, just like that. We're going to jump up over here. Find some nice real estate to work it on, if this thing will ever start working right. There it is. So we're going to see if we can paste it in. And, oh, that's not the right one. Let's copy that again and try it again. There it goes. And now we can start working on our problem. Now we want to know spring or summer. So let's take and write this out using some good big kid math. This time we'll say the probability of the event, and the event is going to be spring or summer, is equal to the odds of spring or summer out of the total outcomes. That means that the odds of spring was going to be, let's see here, we have 24 plus the odds of summer, that was going to be 34. Actually, that's 0.24, my bad, 0.24 and 0.34, and that's going to be out of all of them combined, and all of them combined should be 1, but let's make sure. So to make sure, I'm going to take and just grab my calculator and add them up real quick just to save you all time. So we've got the winner is going to be 0.12 plus spring is going to be 0.24 plus summer is going to be 0.34 plus, and then fall, that's going to be 0.35. You add those all up, and I'm thinking I missed some math here. Let me check that again. I found my issue. It was in summer. Summer is not 0.34. Summer is 0.29. So we need to take and correct this value right here and make that into, come on, work for me, into a 0.29, and it is going to be over 1, and that means you add those up. 24 plus 29, that's going to be, let's see here, 43, nope, 53, so it's going to be 53 out of 1, and they want us to know what's the experimental probability. Well, experimental probability is going to be 53 out of 1, also known as 53%, or also known as 0.53, I think, is the answer they're actually looking for here. So let's jump over to the textbook, put in that 0.53. They're wanting it as a fraction apparently, so we're going to give them the fraction answer, which is going to be 53 over, actually be 0.53 over 1, so it's going to be, let me fix that, 0.53 over 1. There's the answer we want. No, what's it going to be? What they say? They just, why they give us a fraction box if they wanted it as a decimal? Makes no sense. Either way, y'all understand how it works now. And now we're on our last set of examples. Example 5 says a baseball player's batting average is found by writing the ratio of the player's hits to their total number of time at bats, and then writing that ratio as a decimal. A player with the highest career batting average in history had 400,189 hits out of 11,434 times at bat. Based off this relative frequency, how many hits can he expect in a season where a player has 500 times at bats? This is where the rubber meets the road, guys. This is where the problems get pretty exciting. So the player that has the highest number, we're going to have the ratio is going to look like that. So we got that part set. We compare the number of hits to the number of times at bats. Now we're going to use a relative frequency and a proportion, love working with proportions, to find the number of likely hits out of 500. Are they going to use a cross product? Tell me they are. Whoops, go back here. I think I missed something. Scroll down. Here we go. Hold on. All right, the problem said they could estimate, and since they could estimate, they changed this number here to be 11,500. And then they took and no, we're just not doing it that way. We're going to do it Mr. Reach's way. Tell you what, we'll do a variation of the two. They decided that because they're estimating, they were going to leave the 40,189 alone, and this number here, they rounded up to be that. The reason they chose that is because they wanted something that was divisible by that number right there, which was 500. If you were to take the 11,500 and divide it by 500, you'd find that 500 goes into that 23 times. Now you could rewrite that as being 11,500 times 23 equals, divided by 23 is equal to 500. Likewise, if I'm dividing the number on the bottom by 23 to get to its answer, we could also go up here to that 4,189 and divide it by 23 as well. And when we divide 4,189 by 23, what are we going to get? 4,189. Whoops, missed that one. Let's try it again. 4,100. Let's clear it all out. It's not clearing good. 4,189 divided by 23 is equal to approximately 182. And that is where the textbook got the 182 from that's in their answer. And with that, we're at our last problem. This one belongs to you. We're based on admission records. We're doing this together. The last 5 years of college determined that of the 5,260 acceptance letters sent out, 4,734 students attended their college. This year they plan to send out 900. They want to know how many students they can expect to ascend. About, and that's a magic word that allows you to estimate how many of the 900 students who received the letter can they expect to attend. So I set up my proportion that said 4,734 compares to 55,260 as x compares to 900. So from here, we're going to take and do some converting, because we do have that magic about words. I want a number that's close to that number that's going to be divisible by 900. And the answer is going to be 5,400. Of course, the 4,734 is going to stay, and the x is going to stay. Now I can take and say that 5,400 divided by 900, well, that's just going to equal 6. So that I could also now turn around and rewrite that as where I have 5,400 divided by 6. That means it equals 900. And with that knowledge, I can take that number and divide it by 6. 4,734 divided by 6. Grab up our handy dandy calculator because this lesson's taking way too long. 4,734 divided by 6 means that they could expect roughly 789 students to accept. Now let's see how close we are to what they came up with, the way they did it. We're going to type in our 789, hit check, and they came up with 810. That's one of the things about when you're using abouts and estimating, the answers can vary some. With that information, you all get started on your homework assignment. You make sure you give me good quality supporting work, and I'll see you in class tomorrow.